Hello everyone. In this video, Group 15 will be presenting on the finite difference method, focusing specifically on how we solve a nonlinear ordinary differential equation subjected to Neumann boundary conditions. To successfully handle the nonlinearity of this problem, we will be implementing Newton's method to solve the resulting system of equations. As displayed on our cover slide, the specific second-order boundary value problem we are investigating is y double prime equals to 1 over 2y squared. We are analyzing this over a closed interval where x ranges from 0 to 1. Our boundaries are also governed by derivatives set to 0, meaning we are dealing with insulated or zero flux conditions. We will be using a uniform step size of h equals to 0.25 to break down this problem. Now let's move on to look at our core objectives and real-world significance. Before diving into the mathematics, let's establish why this matters. In real-world engineering and physics, systems are rarely perfectly linear. Nonlinear ODEs are essential for modeling complex phenomena like heat transfer involving radiation, advanced fluid flow, and chemical reaction rates. Furthermore, instead of knowing fixed values at the edges, we often only know the flux or slope, which is exactly what Neumann boundary conditions represent. Today, we have 5 distinct goals. First, we will define what makes an equation nonlinear. Second, we will show you how to discretize a nonlinear ODE using finite differences. Third, we will address a common hurdle, handling Neumann boundaries by introducing ghost points. Fourth, we will apply Newton's method to solve the final system. And last but not least, we will bring it all together with a fully worked mathematical example. To solve a continuous differential equation numerically, our very first operational step is grid setup and discretization. We must transform a continuous domain into a finite set of points. For our problem, the domain spans from x equals to 0 to x equals to 1. With our specified step size of h equals to 0.25, we divide this interval into 4 subintervals, giving us a total 5 discrete breakpoints. Now looking at the grid map on the slide, our boundaries are fixed at x0 equals to 0 and x4 equals to 1. This leaves us with 3 critical interior points, which are x1 at 0.25, x2 at 0.5, and x3 at 0.75. Our ultimate goal is to calculate the unknown values of y at each of these 5 specific coordinates. Now, let's look at how we set up the algebraic equations for this bit.
Hi, Assalamualaikum. My name is Nu'afifah binti Sulung. Alright, so to solve this problem using the finite difference method, we first need to approximate the second derivative. We do this using the central difference formula, which uses the values at the neighboring grid points on both sides of a node. The approximation is given by y double prime is approximate yi minus 1 minus 2yi plus yi plus 1 over h squared. Right, so next we substitute this approximation into our original differential equation, y double prime equal to 1 over 2 y squared. Since the step size is 0.25, we have 1 over h squared equal to 16. After substitution and simplification, we obtain 16 in bracket yi minus 1 minus 2yi plus yi plus 1 equal to 1 over 2yi squared. This equation is called the discrete form of the original differential equation. Now that we have obtained the discrete equation, we can apply it to each interior nodes to form the nonlinear algebraic equation. Alright, so after substituting the central difference formula into the differential equation, we obtain the general descriptive form shown at the top. Alright, so next we apply this equation to the interior nodes, which are I equal to 1, I equal to 2, and I equal to 3. For example, when I equal to 1, we obtain 16y0 minus 32y1 plus 16y2 minus 1 over 2y1 square equal to 0. Right, so the same process is then repeated for I equal to 2 and I equal to 3, giving the other two equations shown on the slide. Alright, so at this point, we have obtained the equation for the interior nodes. Next, we will incorporate the Neumann boundary condition using the ghost point method.
My name is Naim, and now I will explain on Neumann boundary condition y prime of 0 equal to 0, Gauss point method. So let's now see how we handle the left boundary condition at x equal to 0, where y prime of 0 equal to 0. Because the finite difference formula for the second derivative needs point on both sides, we introduce a Gauss point, an imaginary point x negative 1 just to the left of our domain. We call its value y negative 1. The Neumann condition y prime of 0 equal to 0 is approximate with a central difference y1 minus y negative 1 over 2 hash equals 0, which gives us y negative 1 equal to y1. That's the key relation. The Gauss value equals the first interior value. Now we write the ODE at the boundary not I equal to 0. So y null double prime equal to y negative 1 minus 2 y null plus y1 over h square equal to 1 over 2 y null square. Then we substitute y negative 1 equal to y1. It will become y1 minus 2 y null plus y1 over h square equal to 2y1 minus 2y null over h square equal to 1 over 2y null square, with h equal to 0.25, h square equal to 0.0625, so 1 over h square equal to 16. Then we multiply both sides with 16, then we get 32 in bracket y1 minus y null equal to 0.5 y null square. Finally, bring everything to one side, then we got 32y1 minus 32y null minus 0.5 y null square equal to 0. That's our nonlinear boundary condition for y null. Notice the Gauss point is eliminated, only real unknown remain. The little diagram on the bottom right show the Gauss point linked to y1. Now let's move to the right boundary. For the right boundary at x equal to 1, the process is symmetric. We add a Gauss point x5 with value y5 to the right of the last node x4. The Neumann condition y prime of 1 equal to 0 gives y5 minus y3 over 2 hash equals 0. Then it becomes y5 equal to y3. Now we can write the ODE at I equal to 4. y4 double prime equal to y3 minus 2y4 plus y5 over h square equal to 1 over 2 y4 square. Then we substitute y5 equal to y3, and we get y3 minus 2y4 plus y3 over h square equal to y3 equal to 2y3 minus 2y4 over h square equal to 1 over 2 y4 square. Then we multiply by 16 again, and we get 32 in bracket y3 minus y4 equal to 0.5 y4 square. Then we rearrange, we get 32 y3 minus 32 y4 minus 0.5 y4 square equal to 0. So it is exactly the same exactly the same form as the left side, but with indicate shifted. The Gauss point method elegantly turns a boundary condition into an equation that fit our system. Both boundary equations are now ready together with interior equation from earlier. We have a nonlinear system for all 5 unknown. That's all. Thank you.
Hi, my name is Mama Azim. I would like to explain about Neumann BC one-side difference. In the Neumann boundary condition, we are given the slope of derivative at boundary, namely y prime 0 and y prime 1. However, the boundary value y0 and y1 themselves are unknown. Therefore, we need to appreciate the derivative using finite difference formula. So as we can see, y prime 0 equal to 0, we can use the formula of y1 minus y0 over h. equal to 0, and we will get y1 equal to y0. That goes same for the y prime 1, which is y4 minus y3 over h equal to 0, and we will get y4 equal to y3. And the next step is substitute into the interior node for I1 and I2. As we know, y0 equal to y1 and y4 equal to y3, so we just need to substitute all the information. So for the I1, we will get negative 60 y1 plus 60 y2 minus 1 over 2 y1 power of 2 equal to 0. And for the I3, we will get 60 y2 minus 60 y3 minus 1 over 2 y3 the power of 2 equal to 0.
Okay, my name is Chong Bing. Now I present the Newton's method. Let's look at how we solve these complex equations. We are using a classic approach called Newton's method. Simply put, Newton's method is a way to find the right answer through continuous corrections. First, we define our unknowns as a vector y and our equation as a function f. The cure formula is shown here. The logic is simple. We start a guess and then we calculate how far off we are. This adjustment is called delta y or the correction. In practice, we do this in two steps. First, we calculate the correction delta y. Second, we add the corrections to our old guess to get a better updated answer. We repeat this process until delta y becomes so small that it is close to zero. That means we have successfully found our exact solution. Okay. The most critical part of Newton methods is dealing with the Jacobian matrix. If you look at the prime times prime matrix on the left, it looks a bit complex. However, it has a beautiful feature called the trigonal structure. This means that aspect of the main diagonal and the two lines next to it, all other position is the matrix are just zero. This mostly zero feature is a massive advantage for us. If it were a normal matrix full of numbers, the computer would run very slow. But because our matrix is so clean, the calculations become super fast. This makes our progress highly efficient and it will easily handle much larger systems in the future. Finally, let's look at our actual result. We started our simulation with a very simple initial guess of all ones. If you look at the history on the left, the error drops dramatically in just the first two steps. By step 5, the correction is also zero. This means our algorithm found the correct answer in just 5 iterations, provided it is highly efficient. The graph on the right shows our final solution curve. As the position moves from 0 to 1, the value of y swiftly drops from 0.873 to 0.809. In conclusion, this smooth curve and the ultra-fast calculation speed show that our method is highly successful and the results are completely reliable.
Hi, my name is Muhammad Faiz Najmi, and now I'm going to cover for the solution interpretation. Now, looking at the numbers, y decreases from 0.873 at x equal to 0 to 0.809 at x equal to 1. It is a drop of only 0.064, so the curve is almost flat. Why is it flat? It is because we have a Neumann conditions at both ends, which is y prime 0 equal to 0 and y prime 1 equal to 0. So the slope is both 0 at both boundaries, and the solution must be nearly horizontal. However, our question is y double prime is equal to 1 over 2y squared. Since y squared is positive, the second derivative cannot be 0. That means there must be a tiny bit of curvature.
We verified that y prime 0 and y prime 1 are both close to 0 and the residual is less than 0.000001 at every grid point. Let us summarize everything that we have covered today. First thing first, the finite difference method converts our differential equation into the algebraic equation at a discrete grid points. Next, Neumann boundary conditions require a ghost points. That is imaginary points that is outside the domain, and it is used to approximate the derivative at the boundaries. Third, the y squared term makes our system nonlinear, so we cannot use a direct linear solver. Fourth, we apply Newton's method, that is an iterative solver that updates our guess using the Jacobian matrix. Fifth, our Jacobian is 5 times 5 matrix and a tridiagonal, which makes it very efficient to solve. And last, our solution converge in just 5 iterations that give a nearly flat curve from 0.873 to 0.809. This combination of finite difference method, Newton's method, and the Jacobian matrix works for any nonlinear boundary value problem. That brings us to the end of our presentation. We'd like to thank everyone for listening and paying attention throughout our session today. Thank you very much.